Regularization. Introduction. One of the most common problems data science professionals face is to avoid overfitting. Have you come across a situation where your model performed exceptionally well on trained data, but was not able to predict test data? Or you were on the top of the competition, on the public leaderboard, only to fall hundreds of places in the final rankings? Avoiding overfitting can single-handedly improve our model's performance. What is regularization? The term regularization refers to a set of techniques that regularizes learning from particular features for traditional algorithms or neurons in the case of neural network algorithms. It normalizes and moderates weights attached to a feature or a neuron so that algorithms do not rely on just a few features or neurons to predict the result. This technique helps to avoid the problem of overfitting. To understand regularization, let's consider a simple case of linear regression. Mathematically, linear regression is stated as below, where y is the value to be predicted. x1, x2, xn are features that decides the value of y. w0 is the bias. w1, w2, wn are the weights attached to x1, x2, xn relatively. Now to build a model that accurately predicts the y value, we need to optimize above-mentioned bias and weights. To do so, we need to use a loss function, and find optimized parameters using gradient descent algorithms, and its variance. The loss function called the residual sum of square is mostly used for linear regression. Here's what it looks like. Next, we will learn bias, or intercept, and weights, also identified as parameters and coefficients, using the optimization algorithm, gradient descent, and data. If your dataset does have noise in it, it will face overfitting problem, and learned parameters will not generalize well on unseen data. To avoid this, you will need to regularize, or normalize your weights for better learning. Why regularization? Regularization is often used as a solution to the overfitting problem in machine learning. Common causes for overfitting are 1. When the model is complex enough that it starts modeling the noise in the training data. 2. When the training data is relatively small, and is an insufficient representation of the underlying distribution that it is sampled from, the model fails to learn a generalizable mapping. Regularization helps us overcome the issue of overfitting. Types of regularization. Based on the approach used to overcome overfitting, we can classify the regularization techniques into 3 categories. Each regularization method is marked as a strong, medium, and weak, based on how effective the approach is in addressing the issue of overfitting. 1. L1 regularization. 2. L2 regularization. 3. Dropout. L2 regularization, ridge regression. Ridge regression is also called L2 norm or regularization. When using this technique, we add the sum of weights square to a loss function, and thus create a new loss function which is denoted thus. As seen above, the original loss function is modified by adding normalized weights. Here normalized weights are in the form of squares. You may have noticed parameters lambda, along with normalized weights. Lambda is the parameter that needs to be tuned, using a cross-validation dataset. When you use lambda equals O, it returns the residual sum of square as loss function which you chose initially. For a very high value of lambda, loss will ignore core loss function, and minimize weights square, and will end up taking the parameter's value as 0. Now the parameters are learned using a modified loss function. To minimize the above function, parameters need to be as small as possible. Thus, L2 norm prevents weights from rising too high. L1 regularization, lasso regression. Also called lasso regression, and denoted as below. This technique is different from ridge regression, as it uses absolute weight values for normalization. Lambda is again a tuning parameter, and behaves in the same as it does when using ridge regression. As loss function only considers absolute weights, optimization algorithms penalize higher weight values. In ridge regression, Loss function along with the optimization algorithm brings parameters near to zero but not actually zero, while Lasso eliminates less important features and sets respective weight values to zero. Thus, Lasso also performs feature selection, along with regularization. Dropout. Dropout is a regularization technique used in neural networks. It prevents complex co-adaptations from other neurons. In neural nets, fully connected layers are more prone to overfit on training data. Using Dropout, you can drop connections, with 1p probability for each of the specified layers. Where p is called keep probability parameter, and which needs to be tuned. With Dropout, you are left with a reduced network, as dropped-out neurons are left out, during that training iteration. Dropout decreases overfitting, by avoiding training all the neurons on the complete training data, in one go. It also improves training speed, and learns more robust internal functions, that generalize better on unseen data. However, it is important to note that Dropout takes more epochs to train, compared to training without Dropout. If you have 10,000 observations in your training data, then using 10,000 examples for training is considered as one epoch. Along with Dropout, neural networks can be regularized also using L1 and L2 norms. Apart from that, if you are working on an image dataset, image augmentation can also be used, as a regularization method. For real-world applications, it is a must that a model performs well on unseen data. The techniques we discussed can help you make your model learn, rather than just memorize.
If you have any doubts regarding this topic, please comment down below. I will respond as per my best. Signing out.